Okay, so in this section of notes, we're going to go ahead and go through the next few sections here of Unit 3, which is going to include basically all of the stuff about gases. So we've spent some time talking about intermolecular forces. We did types of solids. So in this section, we're going to talk about gas molecules, how they behave, and different properties of those gas molecules and how they are related. So let's go ahead and get started. Okay, so let's go ahead and start just with taking a look. This is in section 3.3 of your notes, taking a look at just the different states of matter. So I'm not going to talk a lot about this, but just make sure you notice in these diagrams the difference between our solid molecules and how they're all tightly packed together, our liquid molecules, how they're a little more loosely arranged, and how our gas molecules have a lot of space between them. So when we're talking about our gas molecules today, we're going to be talking about different properties like pressure. So when we talk about the pressure of gases, when gas molecules move around, they move around more than our solids, liquids, and gases do. I'm sorry, solids and liquids only. Gas molecules move around a lot more. And when they move around and they bump into the sides of the container, they create a certain amount of pressure. And so we're going to be talking about that pressure and what causes that, what causes it to change. So we're going to be talking about pressure. We're going to be talking about volume of gas, which is how much space it takes up, and also the temperature of gases and how all three of those things are related. So they're all connected together when we talk about gases, and so there's lots of equations that are going to go along with that. All right, let's first talk about how we measure pressure. So gas pressure is measured in units of atmospheres, which 1 atmosphere of pressure is the same thing as saying 760 millimeters mercury. So what that means is, or how that was originally measured, was they used what is called a barometer, and a barometer is just a little tube that's kind of inverted into a liquid, and the gas pressure from the air pushes down on that liquid, and the liquid goes up the barometer and it reaches a certain height. And whatever height that is represents the pressure of the air around it. So standard pressure is 760 millimeters mercury, meaning that the mercury was pushed up the barometer 760 millimeters. And then we just rename that as 1 atmosphere of pressure. Torr is just the guy who kind of did that experiment, so sometimes they also call it torr as units for pressure as well. You will see both. So that's a conversion factor if we need that to convert from millimeters mercury to atmospheres. All right, so we're going to get into a lot of different equations here in the next little bit about relationships between different properties of gases. So we're going to start with, it's called Boyle's law. You don't have to know the names of the laws, but you do need to know the equations and how those different properties are related. So important things to remember: if this equation has pressure and volume, that means our temperature is going to stay constant. It isn't going to be changing at all. So in this relationship, what happens is our pressure and volume are inversely related to each other. So if we look at this container over here on the left, if I have gas that's taking up a certain amount of space and I increase the pressure on that gas, it's going to decrease the volume. So increase the pressure is going to decrease the volume. That's an inverse relationship when they do the opposite thing. So this graph over here shows that inverse relationship. This equation shows everything, all of the pressure and the volume before. That's what the ones represent. The initial pressure, the initial volume, is going to equal the pressure and the volume after when they are multiplied together. As far as units here, it doesn't really matter. For pressure, it can be atmospheres, it can be millimeters mercury. It doesn't matter what the units are as long as they're the same on each side of the equation. So if you plug in atmospheres on the left, you have to plug in atmospheres on the right. Volume, same thing, units don't matter as long as you keep them the same on each side. So you could use milliliters or liters for this equation. And when you guys come to class next time, we're going to be doing lots of practice with these equations. So right now I just want you to kind of recognize them and know what all of the different parts represent. Okay, in our next equation, we're going to be looking at the relationship between volume and temperature. So since I have volume and temperature in this equation, what's actually staying constant here, this is a typo, this is going to be at constant pressure. So whatever's, sorry, that looks terrible, pressure. Whatever's not part of the equation is the thing that has to stay the same. So here's the idea. If I have this container of gas over here, and this little lid is able to move up and down, if I increase the temperature from left to right here, I increase the temperature, that's going to cause those gas molecules to have more energy. And since they have more energy, they're going to be moving faster, they're going to create more pressure on the lid here, and it's going to push that up in order to relieve the extra pressure that's there. And so the volume is going to increase. Really important here with volume, milliliters or liters is okay. With temperature, has to be in Kelvin. If you do not plug in your temperature in Kelvin, you plug in degrees Celsius, you're going to get the wrong answer. So just a quick reminder that our Kelvin temperatures are our degrees Celsius plus 273. So again, everything over on the left represents our volume and temperature initially. So this would be all of my V1, T1 over here. And then after I heat it up and I change the temperature, what is the new volume going to be? That's going to be after I change those things, and the pressure stays the same. Okay, we have a similar relationship with pressure and temperature. This is going to be constant volume. So this is going to be a direct relationship. So if I increase the temperature, that is also going to increase the pressure if the volume stays the same. So you'll see a lot of questions where it'll say a rigid container. When they say rigid container in your questions, that's their hint to you that the volume isn't going to change. So this container is the same size no matter what. So if I heat up the gas that's in that container, those gas molecules are going to move a lot faster. They're going to collide with the edges of the container more often. So you're going to have more collisions. More collisions means more pressure. Those collisions are also going to have higher energy because they have higher temperature. And temperature is just a measurement of kinetic energy. So because those things are going to increase, the pressure is going to increase as well. Units for this, pressure, you can plug in atmospheres or millimeters mercury as long as it's the same on each side. Again, just like our last equation, you have to plug in your temperatures as Kelvin. All of these equations, all these relationships are based off of Kelvin temperatures, so make sure you're plugging those in. Okay, we have one more here, and this is going to relate volume and our number of moles. Volume can be in milliliters or liters, same on both sides, and represents our number of moles. So basically, this is called Avogadro's law because Avogadro said that the volume that a gas takes up is completely dependent on how many moles there are. So if you look at this statement, this statement over here says these balloons, so we've got hydrogen, nitrogen, oxygen, these balloons all have the same volume, and if they have the same volume, that means they have the same number of molecules, which also means that they have the same number of moles. Remember, 1 mole equals 6.02 times 10 to the 23rd molecules. So if you have the same number of molecules, you also have the same number of moles. So you can use this equation to calculate or figure out that relationship, but you're going to have temperature and pressure stay constant in order to use this equation. All right, so we've got the combined gas law kind of puts all of those things together. So if none of those three things stays constant and all three things are changing, pressure, volume, temperature, then you can set it up equal to each other this way. It looks like basically it's called the combined gas law because it takes basically Boyle's law and Charles' law and it puts them together into one equation. So when you're looking at an example, you have to figure out which equation to use. That's probably the hardest part. After that, you're just plugging in numbers and figuring out what your answer is. So in this example, it says an inflated balloon with a volume of 0.55 liters at sea level, which has a pressure of 1 atmosphere, is allowed to rise to a height of 6.5 kilometers. That's just extra information, not anything I have to plug in. But at 6.5 kilometers, that pressure is 0.4 atmospheres. So assuming the temperature remains constant, that's important. So we then need to calculate what the new volume of the balloon is. So if the temperature remains constant, if you're using this combined law equation, anything that stays constant can just be crossed out of that equation, and then your equation that you're going to use is just whatever you have left over, which is P1 V1 equals P2 V2. As you go through these problems, it's helpful, and what you should do is you should spend some time actually listing everything that's given to you in the problem as you read through it. So as I look through this question, it says an inflated balloon with a volume of 0.55 liters. So that means my initial volume, my first volume of the balloon is 0.55 liters, and that pressure is 1 atmosphere. And then it says it rises and the new pressure is 0.40 atmospheres. And it's asking me for the new volume of the balloon. So I want to see this set up for all of your gas law problems. Because once you have that set up, then plugging everything in to actually solve the problem is a lot easier. So I have my P1 is 1 atmosphere. My V1 is 0.55 liters. And that equals P2, which is 0.4 atmospheres, and then V2, which is what I'm looking for. So you need to divide both sides by 0.4, and that will give you V2, which is 1.4 units. Since I had liters right here, that means the unit that I'm solving for is also going to be in liters. Okay, so you need to go through, look at the problem, see what you're working with, see what variables you have to plug in, see what's constant, figure out what equation to use, and go from there. Okay, so in our next section, we're going to look at really important equation in AP Chemistry. The ideal gas law shows up over and over again, relates all of the properties that we just talked about. So P is pressure in this equation. The difference with the ideal gas law is that the units that you plug in are very specific. You have to plug in atmospheres for pressure in this equation. For our volume, you have to plug in liters. You cannot plug in milliliters. You can't plug in anything else. N represents our number of moles, and T is temperature, which has to be in Kelvin, just like in our other equations. Now, R is what is called the ideal gas constant. And it's a constant number that's given to you all the time that you plug in the same number every single time. And it relates all of these things together: pressure, volume, moles, and temperature. So our number for the ideal gas constant is 0.08206 liters units, atmospheres, liters over moles, Kelvin. This is our number that gets plugged in for R every single time. Okay, so what we're going to go ahead and do is just do an example with that really quickly. Oh, up here, STP, an important thing for you guys to know. STP represents standard temperature and pressure. So you guys need to know what those numbers are. So if ever they say in a problem at STP, that means standard temperature pressure, which means 0 degrees Celsius, which is 273 Kelvin, and then 1 atmosphere of pressure. Okay, that'll show up. So those are just kind of numbers that you need to memorize here. The equation's really easy to use. Look at this example over here. It says calculate the pressure in atmospheres exerted by 1.82 moles of gas in a steel vessel. The volume is 5.43 liters, 69.5 degrees Celsius. So I'm looking to solve for pressure in this problem. So I want you guys to show your equations rearranged. So when I rearrange to solve for pressure, I have nRT over V, and then I can just go ahead and plug in my numbers from there. So 1.82 is my number of moles, pressure 0.08206, sorry, that's R. Temperature needs to be in Kelvin. I cannot plug in 69.5 degrees. I need to plug in that temperature in Kelvin. So that temperature in Kelvin is 342.5. So just add 273 to that number. And then divided by my volume, which is 5.43 liters. And then you can go ahead and solve for your pressure. And you get a pressure of 9.42. We're talking pressure here. My units are in atmospheres. So that's my answer. All right, let's go ahead and move on a little bit from all those gas law equations. We are going to practice those a whole bunch in class. But let's talk about something called partial pressure and mole fraction. So basically, these things are going to apply when we're talking about mixtures of gases. So over here in this container, I have 2 gases in the same container. And they'll ask you, what is the partial pressure of gas 1? What is the partial pressure of gas 2? It doesn't matter. The fact that they're combined doesn't change how much pressure the gas exerts if it were by itself. So if I know the pressure of gas 1 by itself, and I know the pressure of gas 2 by itself. When I combine them into the same container, the pressure is just going to be those 2 pressures added together. So that's all you need to do. And then you can calculate them separately using the ideal gas law if you need to, and then add them together. But basically when you mix them together, it doesn't change the pressure that they exert by themselves. So when we deal with mole fraction is also dealing with mixtures. So even though it's called mole fraction, you're actually going to be giving answers in decimals, okay? It's not going to be a fraction. It's not going to be a fraction. It's also not going to be a percent. So your answers are going to be in decimals here. So it's really just a ratio. So we've got these 2 equations here. These 2 equations are given to you on your reference sheet, so you don't need to memorize them, but you need to know what they represent. You need to know what to do with them. So when we're dealing with mixtures, so let's look at this example. A mixture of gases contains 4.46 moles of neon, 0.74 moles of argon, and 2.15 moles of xenon. And then we're asked to go ahead and calculate the partial pressure of the gases. If the total pressure of all of them in the mixture put together is 2 atmospheres, so that means the pressure of neon plus the pressure of argon plus the pressure of xenon all equals 2.0 atmospheres. Okay, I'm going to go ahead and actually just do this for one of the gases because the procedure is going to be exactly the same no matter what. So I'm going to find first my total number of moles. So I have 4.46 moles of neon. I've got 0.74 moles of argon and then I've got 2.15 moles of xenon. So together, I have 7.35 total moles of gas, okay? So if I want to find the mole fraction of, let's go ahead and just do neon. Okay, if I want to do the mole fraction of just neon, so X represents mole fraction, and then I can go ahead and just put the symbol of the element I'm looking for the mole fraction for right next to it. So I'm going to take my moles of what I'm looking for, which is neon. Neon had 4.46 moles. And I'm just going to divide it by my total number of moles, which is 7.35. That gives me a number of 0.61. That's my answer for mole fraction. Mole fraction is one of the only numbers where there are no units, okay, because it's basically a ratio of how many moles of one thing you have compared to the whole mixture. Okay, the next question was calculate. Oh, it actually didn't even ask us to calculate the mole fraction. It just asked us to calculate partial pressure. Well, I couldn't calculate partial pressure until I knew the mole fraction. So if I want to calculate the pressure of neon in that sample, I'm going to take my total pressure, which was 2 atmospheres, and I'm going to multiply it by the mole fraction, because basically if whatever fraction I have of moles, that's what fraction of the pressure that particular gas is going to provide. So I can just take that total pressure, multiply by mole fraction, and get 1.22 atmospheres as my partial pressure of neon. All right, for this practice, really quickly, I have this on here. Each shape represents a different gas. Calculate the partial pressure of each one. So the AP exam loves to do things where you just have to count shapes. So they're going to ask you to calculate the partial pressure of each, which means that you need to find the mole fraction of each. So you'll need to find the mole fraction of circles, the mole fraction of triangles, and the mole fraction of squares. So instead of elements, we're just doing shapes. And since they don't give us numbers of moles, we're just going to count. So I started with circles first. 1, 2, 3, 4, 5 circles. And then total shapes, there are 5, 6, 7, 8, 9, 10, 11 shapes. Triangles, there are 4 out of 11. And squares are 2 out of 11. So then you can just divide those out and get your mole fraction number, which is 0.36 for my triangles, 0.18 for my squares, and then 0.45 for my circles. And then all I have to do is go ahead and take that total pressure and multiply it by the mole fraction. That will give me the pressure of just the one thing. So the pressure provided by just the squares, whatever element that represents, is that mole fraction multiplied by the total pressure. So then it's 0.47 atmospheres, and you would do the same for all of the rest of those. All right, this is the last slide we're going to go through, or the last section of your notes, 3.5. So the kinetic molecular theory basically just talks about properties of gases that we kind of always assume are true. We assume that it's really about the volume of the empty space, not the particles themselves. As we're talking about gases, those particles are constantly moving, that they don't exert forces on each other, which we know that they do. They have intermolecular forces. We're going to talk about that later, but right now we're talking about ideal gases. We pretend like none of those things happen. This one, number 4 here, is really important. It is the relationship between kinetic energy and the temperature. So kinetic energy is just specifically a measurement, or temperature is a measurement of the kinetic energy. So if gas molecules are at the same temperature, they have the same kinetic energy all the time, no matter what. So if you have hydrogen gas or helium gas or nitrogen gas, whatever it is, if they're all at, 300 Kelvin, then they all have the same kinetic energy because it is completely dependent on temperature only. Okay, that's kinetic energy. Kinetic energy is different than velocity or how fast something moves. Although you don't need to know this equation yet, kinetic energy takes into consideration both mass and velocity. So same temperature, same kinetic energy. That's what you need to remember. Okay, that's a key thing. However, velocity is a little bit different. So if we're talking about how fast they're moving, lighter molecules are going to move faster at the same temperature, because if they have the same energy, but lower mass, that velocity number is going to increase to get that same kinetic energy. It's easier to move things that are lighter, so you need to remember those two things. Lower molar mass means greater velocity, but also if they're at the same temperature, then their kinetic energy is the same. And two terms here that you need to know, diffusion and effusion, basically just has to do with how gas molecules spread out over time, okay? So I've got two diagrams down here that are really good at just showing you what's going on with these two things. So diffusion is the whole idea of if I have a gas molecule in a smaller container over here on the left, and then I remove this barrier, those gas molecules aren't going to stay on the left side. They're going to spread out evenly. Okay, so the spontaneous mixing of gases or spreading out of gases to fill the container, just because molecules move. Effusion is kind of the same idea, and that is if you have a little opening in the container, those gas molecules are going to go through that little opening and spread out into the other side. You need to know those definitions. You also need to know this right here. They'll ask you which one will spread out faster, which gas will, diffuse or effuse more quickly. The lighter they are, the easier they are to move to the other side. So lower molar mass equals faster rate of effusion. Okay, so that's it for you guys for today. Come back to class and we'll be using those gas law equations to do calculations and talking some more about molecules, gas behavior. All right, so I'll see you guys in class.